is usually the fourth Monday of the month. So that would be this one, the Data Science SIG. So we want to make it great for networking, announcing jobs, getting hired. Just for a show of hands, how many people is it their first time tonight at ACM? Great, great. Shout out if you heard about it somewhere besides meetup.com. Anywhere else? Yeah, go ahead. Oh, colleague, okay. Friend of a friend, great. Oh, college. Oh, okay, good. And so on our YouTube channel, we have about 130 of our past talks. So you can check that out. That has a lot of good content. Some of our upcoming ACM events. On May 1st in Saratoga, we have the origins of Silicon Valley. Why and how it happened here. And then on Saturday, we have a day-long training class that charges about $150 depending on how soon you sign up. And that'll be in Sunnyvale. And that's on Kubernetes distributed TensorFlow. All right, Kubernetes and distributed TensorFlow on Kubernetes. So for using distributed TensorFlow. Bharav has taught a variety of data science classes, deep learning classes. Then on Wednesday the 22nd in Santa Clara, we have emerging AI applications and infrastructure systems with active storage class memory. And then June, I'm still working on booking that speaker. In July, we have at Walmart Lab Sunnyvale here, best practices in data science on rapid model development and faster production deployment. So that'll be related to Zepl. It's an open source Apache project. So it's kind of like if you like Jupyter Notebooks, only think of something that supports also R and a variety of other languages besides Python. So those are some of our upcoming events. Also tonight, raise your hand if you're an ACM member of the local chapter. Great, so we'll have a drawing for a couple of books here. So I was at one of the local conferences with O'Reilly and Cloudera, the Strata conference. So O'Reilly supports our chapter by donating books for raffles. More details on the workshop on Saturday, Kubernetes and distributed TensorFlow. So it's a one day, 8-hour boot camp that'll cover deep learning introduction. So these are some of the bullet points. If you're interested, go ahead and take a picture or look at our meetup site. You have to sign up, not on the meetup site, but there'll be another site link that you go to sign up and pay. So that'll be through Eventbrite, but go ahead and take a picture. So we're a local nonprofit. Some of the things we do besides talks and training classes is we also judge in the science fair. So there's a Synopsys Science Fair results. We had judging on Thursday, March 14th. So those are some of the ACM winners. So it's for all of Santa Clara County, both middle school and high school students for each grade. We were judging and giving awards. So we had to review 1,500 projects over 15 ACM judges. There's lots of opportunity to do it next year. Raise your hand here if you were one of the judges or participating in this science fair. So there's Tom, who was one of the organizers. Thank you very much. So if you can imagine 15 judges over 1,500 projects, that's what? Each judge reviewing 100 projects. Yeah. That's the first pass. And we go back for a second pass with the second judge to get a better opinion and have a closer look. So the biggest award, we were awarded about 2,600. The biggest award was 640 for the student, and we also like to support the teachers. So we gave 160 for the teacher. This was a sensor with a phone app and a signal processing computer, and it was measuring asthma respiration. So there was also a lot of machine learning and AI projects. Many of them apply to medical. You know, one title that Tom remembered was genome markers in cancer. So just imagine if you were in high school and you were working on that as a science fair project and you weren't first place winner. So a lot of good things going on here. So now I'll pass a microphone to the audience. I just wanted to invite people to announce if their company is hiring or if there's other interesting meetups or local events. Is there anybody who wants to pass a microphone through the audience? So I'll just go from one side of the room to another. Raise your hand if you want to make an announcement. Say your company is hiring or some other interesting meetup. Nobody's hiring? Oh, come on up. I'd like to also thank Walmart Labs for use of the facilities and, more importantly, sponsoring the pizza.
Thank you. Hope you enjoyed the talks and the meetup. As usual, Walmart Labs is hiring especially data scientists and data engineers. So if you are passionate about being part of Walmart Labs and building the future of retail, please contact me.
Thank you very much. Oh, say your name?
And I'm Gorgon.
Okay, thank you. So, any other hiring announcements? Okay, come on down.
I'm Joe from Realtime Media, and we actually built and open sourced this stuff what I was going to talk about today. We are definitely hiring. If you are interested in this stuff, please reach out.
Okay, very good, thank you. So just as a suggestion, if the people that are hiring maybe gather together afterwards by the orange box, then anybody can find you there. One choice. So raise your hand. Any other announcements? Any other hiring? Any other cool meetups or conferences in the area to talk about? Okay. So if you're interested in being an ACM volunteer, we've got about a dozen people, such as myself, that we meet once a month over dinner, the first Monday of the month. We buy the volunteers dinner. We work on planning of the upcoming events. You might have an interest more in marketing, promotions, editing the website.
Video is off.
The video cable's unplugged.
Oh, thank you.
No. Black cable is white.
Hopefully, you cut it before it hit the ground for you to notice it.
Thank you much. So also, if you're interested in being a volunteer, maybe suggesting speakers, there's different levels you can get involved in. So we're making a video recording tonight, and this will go on our YouTube channel in about 2 weeks or so. So you can check out for it there. That's just youtube.com/sfbayacm. Now, when you ask a question as an audience member, I've asked the speaker to repeat the questions because the microphone won't pick up you in the audience. And so don't give a 2-minute context with a 5-part question because people won't be able to remember to repeat it. So if it's that long and complex, take it afterwards. So keep it to about a 45-second question or whatever the memory limit is of our presenter. So I'd like to introduce the speaker tonight. So stream processing is a simple programming model. It's able to elastically scale. It simplifies operations significantly. We'll be talking about Apache Pulsar, native support for serverless functions. You can deploy it in thread, process, or containers. It's used for data transformation, extraction, routing and filtering. Describe how it can be used on edge computing. So Sanjeev's background at Streamlio focused on next-gen real-time processing engines. Before this, he was tech lead at Real-Time Analytics at Twitter, where he helped co-create Era. Before that, at Locomatrix, working on their engineering stack. Before that, in Google AdSense. He's a master's in computer science from the University of Washington. And there's his LinkedIn profile. Take a picture if you want to reach out and say hi. So please give a warm round of applause for Sanjeev.
Thank you. And by the way, on my resume I listed UW, and UW typically means either University of Washington, or in my case, it's actually University of Wisconsin. That's always a contention. We always fight over it, but that's okay. So I'm always a Badgers fan for those of you from Madison. Thank you, everyone. Let me just connect this. All right, let's see. All right. So it's about serverless, and it's about stream processing. But before we go there, let's take a brief stroll in the history of how data processing in general evolved. I'm not going to bore you too much about it. Just a quick tidbits. So big data, as we all know, began with batch, right? It began with Google writing about their Google file systems, about the MapReduce, and the world of open source, like basically woke up and said, you know what, this is incredibly useful. We see all the same problems that Google is facing, Google faced 5 years ago now. Let's create some of these technologies that Google mentioned, and of these came the HDFS, the MapReduce, the Hives, and so on and so forth. But it began with batch data in mind. That is, you have a bunch of data, you want to store it, and then you want to process it. You want to process all of that in bulk, and therefore, all the technologies, especially all the specifically technologies involved with Hadoop, all optimized on making sure that you have a batches of data. How do you most efficiently store and process huge batches of data at a single time? So that worked well for a while. But then arose a new class of companies like Twitter, companies like Facebook, where people were interacting with their social circle all the time. So from their company's perspective, events were happening all the time. And it was imperative for them to react to those events as quickly as they happen, as opposed to waiting for a bunch of data to buffer up and then process it. They found out, obviously, that the existing big data tools, Hadoop, HDFS, whatever it is, was not adequate for the task. And therefore, we had a whole bunch of new set of technologies, message buses, as well as real-time processing engines. Storm and Kafka are classic examples of that sort of generation where reaction times became important. Now, what do we really mean by real-time out here, right? So the aim, as I said, is to react to events as quickly as possible. And quickly here usually is in terms of milliseconds. There are a whole class of problems where reacting to events as quickly as a nanosecond, and these days picoseconds is important. For example, if you're in high-frequency trading or something like that. So the classes of real-time that we are going to consider here won't cover such cases. We will restrict ourselves to the more mundane millisecond-type real-time systems. What was also established was that events, when they come, they have to be buffered, because the rate at which the events arrive and the rate at which we are able to process or analyze those events, there is an impedance mismatch between these two rates. And therefore, in order to make sure that we actually don't lose this data or make sure that we process all these elements, we have to have some sort of a incoming queue, aka the message bus. And so that pattern was sort of established when the real-time applications, when the real-time tools were set up. And then what's a reaction? A reaction is some sort of an action, like whether you want to enrich something or some kind of an analysis. Hey, you want to compute something like who is on your website, how many people in Indonesia are on your platform at this moment in, say, an appropriate demographic, and something like that. So those are the type of stuff that you want to analyze in real time. So that is an example of an action. So we sort of just graph it out. You have a bunch of incoming messages. You need to somehow do something with them, and then you have some output messages. The output messages need not be messages. They could be some actions. They could be saying, hey, show this ad, for instance, for this type of users. They could be just simply saying, you know what, let me learn about it and tinker my ad serving algorithm so that it better matches the kind of demographics that my website is currently serving, and so on and so forth. Now, how is this compute represented? The first generation of the systems, the first generation of the real-time systems that came up said, you know what, let's go for a DAG-like approach, a directed acyclic graph approach, wherein we have a bunch of data sources where the data is actually coming in. Let's feed them to action pieces where actions represent some kind of an action on these data pieces. And let's chain up these action pieces together and form a DAG, right? If anyone who has had an experience coding in, say, Storm, or for instance, Flink or Spark and so on and so forth, essentially what you're trying to do is to do this kind of a DAG. You're saying, these are my sources. You're saying, these are my actions. And you're saying, you know what? This is how data flows between my sources and my actions. And this is how actions have further consequences. And there are actions to the actions, and so on and so forth. And here is how you stitch your program. You stitch your DAG. And then you say, OK, you know what? Real-time framework. Now keep track of all of these things. Make sure that all of these stages are scheduled appropriately, run appropriately, monitored appropriately. Give me some guarantees about making sure that every data is processed at least once, at most once, whatever my guarantees are, and so on and so forth. If you write these things, let's just say we are going to count the number of words that are coming in. Let's just say you have a pipe of data. The data is just traditional sentences, and you want to count how many times a word appears in a minute, in a second, in whatever time window you have. So in a Storm-like environment, you do this. You do all this stitching by yourself. So this is how the thing gets executed in Storm. You say, you know what? Let's have something that executes. Take a sentence, split the sentences into words, and then further action. Another action is okay. Once the instance is there, once I have my words, I need to make sure that a particular word goes to just one particular place, and it gets counted up. Right? So you express your computation of the actual count somewhere here, and basically this is how you basically stitch up your word count example. Notice how verbose this is, right? You have to define everything of your DAG, and then you have to then execute and so on and so forth, right? This was of course the first generation. This was of course very verbose, and this was of course very easy to get something wrong. Right? But this was, of course, the first generation. Yeah? People thought, you know what? This is right. It's too verbose. How can we make it better? So then came the 2.0 approach. You know what? Hey, look, there are these fancy things like Scala and so on and so forth. They support functional paradigms. Let's actually write the same thing functionally, very compact, very neat. So here is the same word count, but now we are using some sort of a functional programming. So we say, you know what, let there be a new source that generates sentences. We flat map it. Essentially, a flat mapping is take something and emit a list of things. Then you have a reduce by key operation wherein you're going to say, you know what, I get a word, and I just add up the word, and I make the key the word as the key, and I just make it 1. And if there is if the word doesn't exist, if the word already exists, I just say what was the previous value of the word, what was the previous count of the word, and I add it. That's what the x plus y notates. This is very simple, right? I mean, it's just 4 or 5 lines of code. This is definitely a big improvement over this monstrous 2-page kind of a verbose declaration. But notice, say that you're a high school programmer, right? You come up to this code and you are dumbfounded. What is flat map? What is reduce by key? I have no idea. What is all this? So while it is compact, it's very complicated. And it's actually very complicated not only for novices, it's actually complicated even for seasoned programmers. Where should I use map? Where should I use flat map? What is my initial condition for my reduce? Which kind of reduce operation should I use? Should I use a tumbling window? Should I use a sliding window? All of those complications come into place, right? So the takeaway is that, yes, we have made these representation of compute compact, but as a result, it has gotten very complicated. While this was all going on, the messaging and the compute were all emerging sort of separately. So you had the messaging system, let's just say, Kafka or RabbitMQ or ActiveMQ, RocketMQ, or a bunch of other MQs evolving separately. And then you had these compute engines, Flink or Spark or Storm or Heron and so on and so forth. They were evolving separately. So while the separation is good from a bunch of different reasons, the problem is that it is two systems. It's too complicated. You have to manage both the messaging system. You have to manage the compute system. Their purpose is different. Their APIs are different. Their impedance, there is an impedance mismatch when data flows from one system, say the messaging system, to the compute system, and back from the compute system to the messaging system. There's a lot of bolts that you need to fit in order to make sure that you have the most optimal performance. So yes, we have gotten better at expressing our computations at the cost of complexity, but both the programming complexity of understanding what is there and the operational complexity of maintaining these real-time systems became very complicated. Now, at the same time, people are learning lessons. You know what? A large part of transformations are very, very simple. At Twitter, 80% of our transformations were simple ETL. Hey, it's data cleansing. There are a bunch of values that are not present. I need to make sure that I have some default values, whether it is null, whether it is 0, whether it is whatever. I need to ensure that there is something filled for these data. Hey, the time formats are different. I need to make sure that everything is represented as seconds after UTC or milliseconds after UTC or whatever your base normalized value is. Such mundane system, such mundane things. I need to basically route these events based on some kind of a tag this message process, some kind of a key the message hash to or something like that. Right. These were 80% of the problems. And you know what? For all of these simple mundane problems, we had to actually go to a very complex system, use its very complex API, and write it, and then submit it, and then deal with the whole event in impedance mismatch of, hey, you know what, the data is not flowing efficiently, what is wrong, which stage the program is getting stuck, let me debug that, and so on and so forth. So it took a whole amount of time for programmers to actually deploy, start from scratch of what the problem that they had to solve, aka the ETL problems, deploy it, and make sure that it is running in production smoothly, and so on and so forth. Weeks and sometimes even months passed just to sort of, get these milestones. The world was not ticking. The world was not keeping silent, right? I mean, in the rest of the world, there was a new revolution brewing, and that was serverless. One of the things that Lambda got right, AWS Lambda, and now everyone else is sort of already out there. Google has some, Spring has some, and so on and so forth, is that they said, you know what? All systems pretty much scale reasonably well. What don't scale is developers. The most precious resource that we have is not machines. Machines have gotten very simple. I can go, I can use my credit card, I can get 10 EC2 instances or even 100 EC2 instances for a few hours very, very quickly, very, very, relatively cheaply. I don't have to buy any machines and so on and so forth. I don't have to dispose of, I don't have to maintain my data centers. All of that has become relatively cheap. What has become complex, what has become actually very expensive are the developers. I need to make sure that developers are productive from the day go without them having to learn anything, without them having to have 5 years experience of having to actually run and manage a system and so on and so forth. You need to have something where, in serverless, you just write a simple function, you submit to the system, and the submission runs once per event. How and where the things are executed, I don't really care. As long as my function is executed and it produces the right results, I'm happy with it, right? So it's two things that it is buying. The impact of serverless is not just the fact that it's managed by a service provider, aka it's a SaaS as a service, but it's also the programming simplicity. It's the modeling simplicity that it brings with it. And of course, because it was so simple, and because it was implemented in wide variety of languages, starting with JavaScript, Python, Java, and so on and so forth, it became wildly popular, right? So we paused for a minute and said, you know what, what's actually the difference here? Are serverless people doing something dramatically different than what we do in the streaming world? After all, they're both event-driven architectures. Right? In serverless, your function is executed a minute, every time an event is generated. That's the case with even streaming systems, right? I mean, the aim of streaming system is to react as soon as something happens. They can be used both for analytics. They can be used both for serving. They can be used both for transaction system. That's really the power of the underlying system. They both can have composition APIs, right? I mean, you can have a chain of functions programmed together in such a way that one function's output is the next function's input, and so on and so forth, and get a chain of programming the same way that you have a DSL, a map emitting to a fat map, emitting to a reduce, emitting to a sync, and so on and so forth. It's the same concept. It's just expressed differently. It's just expressed as stages of different computations, as opposed to just one line, as opposed to just one line of program. We don't, one of the things that typically say, serverless, we don't care about ordering. That's true of a lot of systems which are most queuing based. In queuing based, items arrive. These are work items. Let's just say people are uploading photos. These are photos that are coming to your stream. And you want to do some pre-processing. You want to, say, generate thumbnails. You want to extract features from those photos, and so on and so forth. It doesn't matter whether you extract the first photo first and the second photo second, and so on and so forth. You can reverse the order. Still, the work is the same. Essentially, you're extracting features from the photo. So it doesn't really matter whether you are doing strictly ordered processing or unordered processing. A lot of, by the way, work that we do inside streaming world is unordered. But whether or not something is ordered or not is just semantics that you should actually be able to express. You should be able to express saying that, hey, you know what? I don't care the ordering of this particular stream. Give me the events, execute these events as the event happens. I don't care about ordering. So you can execute the event second event before the first event. I don't care. On the other hand, if you really care about events, you should be able to say the same framework, you know what? Ordering is important. Make sure that always execute, event number 1, and only after event number 1 is successful, execute event number 2, and so on and so forth. If something fails, do something and come back to the next event, and so on and so forth. You should be able to program this, or you should be able to tell the system to do this. The other thing people say is, hey, you know what? It's pay per action, but that's really just a billing question. It's nothing to do with the technologies per se. So this actually forced us to think, what we really need and what's really needed for most of the applications, for most of the things that heavyweight stream computing engines today are used, is just the simplest possible API. Any programmer, anyone who has had some basic programming experience, no data science experience of any sort, no data engineering experience of any sort, to be able to come and be productive from day one. He or she should just know Java, or Python, or Go, or whatever language that we offer in. And he or she is ready to go from day one. So that way, we can now scale developers. Because as I said, most of the real work is really ETL. It's just transformations and so on and so forth. Anyone should be able to do these things. We should then architect the system based on the message bus native concepts. Right? We should use things like input topics, output topics, and so on and so forth. Because after all, you are acting on a message and on a per event basis, on a per message basis, and these messages may or may not have some outputs, and whatever outputs they have kind of represents some sort of an output topic or an output stream. And we should be able to have various different flexible runtimes to this. I want to run it as a standalone application, or I want to launch this in Kubernetes and forget about it and let Kubernetes manage into it, right? As a developer, I should not care about this. I should write one function, I should just submit it, and the system takes care of it somehow, magically. Well, that's what Pulsar function is. But before we go to Pulsar, let's actually just briefly go over what Apache Pulsar is, because a lot of the constructs of what we use in functions, Apache Pulsar functions, are based on what the capabilities that Apache Pulsar provides. By the way, anytime you have any questions, feel free to ask them. So what's Apache Pulsar? So Apache Pulsar is a pub sub But it's more than a PubSub. It supports unified messaging model. It supports both streaming. You can do streaming with it. You can do queuing with it. It's more like an event store. Events are coming in, and you want to store these events. Maybe you want to store these events for 1 day. Maybe you want to store these events for 1 month. Maybe you want to store these events for 10 years. It shouldn't matter. After all, your events are your data. You never want to delete these events. You never want to mess around these events. You may want to transform these events and have secondary events, tertiary events, enriched events, transformed events, whatever way you want, but you never want to delete your events. So your events should be there in some place, and that is Apache, that is Pulsar. So Pulsar is essentially the system of record, the log of what all happened in your system. That is Pulsar. It should be durable. By default, messages should be saved. And by saved, we don't mean, hey, you know what, it's in memory on some server, and if the server gets doomed after a while, the messages could be lost. No, it should not be like that. By default, Apache Pulsar f-syncs messages on at least 2 machines before returning back to the producer, which means that your messages are always durable. Of course, you can turn it off if durability is not a requirement, but durability comes out of the box as default. It provides guaranteed ordering. It has the same concept of topics and partitions, and data in a partition is always ordered. It supports all the usual mechanisms of at least once, at most once, effectively once, and so on and so forth. So as a consumer, you can be rest assured that you will get the data in this order semantics that you want. You have geo-replication built in out of the box. You don't have to run any kind of separate scripts. You just configure the system, say that, hey, you know what? There are many instances of the system running, each running in its own data center, but make sure that some topics here are replicated in a mesh-like fashion over to another system. And the system should take care of it to make sure that data is replicated. It's very low latency, highly scalable, highly throughput, all the usual shebang.
For the unified message model, what's the difference between a stream and a queue in this?
Sure. So the question was, what's the difference between streaming and queuing? And it has all to do with ordering. So let's just say, a classic example of a queuing is in a work-based model. So let's just say you are a photo sharing app or something like that, right? Users are uploading photos to your website, and essentially your stream of events is a list of photos, is a stream of photos that are being uploaded. Now, before you store these photos, for instance, you want to do some feature extractions. You want to extract faces, for instance, or you want to generate thumbnails, blah, 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 right? Now, let's just say you receive 10 photos. Now, it doesn't matter whether you process the first photo and then only process the second photo and so on and so forth, right? You could have a farm of 10 machines, and all of these 10 machines could be processing all of these, one each of these photos concurrently, simultaneously. And it doesn't really matter who finishes first. Maybe the 5th guy finishes first and goes to the next model and so on and so forth, right? And so that's the queuing model. And here the system is smart enough to recognize that, okay, you know what? There is a pending list. 1 to 10 are pending. 5th got over. Let me give him 11th. But I make sure that, that the 5th is not redelivered to anyone because 5th has already been done. And so as and when people are finished or acknowledge that they have consumed their data, I give in the system. So that's a more queue-like system.
Which one is the order?
That's the streaming model.
The stream is ordered, the queue can be out of order.
Yeah, the queue can be out of order. So in a streaming model, typically what you have is a stream of data, and you typically have just one consumer consuming one partition. So that basically says that it's ordered, and you can actually say, for instance, when you're doing session analysis and so on and so forth, you want to make sure that all the events of a particular session are handled in the order that they happen really in real time, right? So that's an example where you have to make sure that only one consumer is actually handling all the messages of a particular session and so on and so forth. So moving on to a little bit of Pulsar architecture. Pulsar has a 2-layer architecture. So there is producers and consumers, but the serving part is done by what are called the brokers, and the storage, that is the data, actually resides on what are called as the bookies. So brokers are the ones that client interact with. Brokers are the ones where data is actually sent in by the producer or sent to the consumer. But the data actually resides on the machines of the bookies. It's durable, Data is synced to the bookie before acknowledgement is sent back. That's one huge thing that Pulsar, we never lose data. Now, storage and serving are separated. Why is this important? It's important because these are two dimensions that can grow independently. As a classic example, let's just say that you have a stream of data. Your stream of data is ever growing. It's like, let's just say, click stream data and so on and so forth, right? It's, you don't want to ever lose your data. You want to keep your data forever. So that means that your data storage for your stream, your click streams, will always keep on growing. So if you have a 1 year's worth of click streams, that will spread to, say, 100 brokers based on what the data size is. So your bookies, you can now have 100 bookies to sort of store that data. On the other hand, only 2 or 3 consumers might be interested in actually reading that data. So that means that your brokers can only be 2 or 3, right? So this way, you can actually scale the storage separately and in terms of the bookies. On the other hand, you could have different data wherein there is a lot of applications, a lot of people are interested in that data, in which case you are serving the same data repeatedly again and again. Right? So in that case, you sort of become bandwidth oriented. And at that point, what you have is that you can just increase the number of brokers. But the bookies remain only small because the data itself is small. The data itself is, can probably fit in the disk of, say, 3 bookies and so on and so forth. So you can just have the minimal number of bookies, but maximal number of brokers according to your serving requirements. In short, you can actually have brokers and bookies all collapse into one machine. That's possible too. In fact, you can run all of this system in a single JVM, where bookies and brokers are all collapsed into one single process. But it has the flexibility of actually separating them out into multiple processes running on multiple servers if needed. And the other huge difference is that, yeah, go on. So I think that will probably get clear with this thing. So the question was, how do you map bookies and brokers? So that comes to the segment centric. So what we do is that if you're familiar with Kafka, let's just say there is a partition. One particular broker hosts the partition. Is actually the leader for the partition, and the same partition could have followers. So in this particular example, you have a leader and you have a follower, which is called as copy. So a particular broker is handling one partition, and there are 2 other guys who are the brokers. What we do is that we take a different view. We actually take the partition, take the logical partition, and chop it off into time-based segments. And these segments could be size-based, saying, hey, every time you have 10 megabytes or 100 megabytes, chunk it and make it a segment. Or these could be time-based as well. After every 10 minutes and so on and so forth, have a new segment and so on and so forth. Right? So what we do is that we accumulate a segment, and then we pepper the segment across the bookies. So let's just say in this partition there are many segments, 1, 2, 3, 4, 5. 1 is the oldest, 2 is the newer, 3 is the newest, and so on and so forth. Right? We take segment 1. And we pepper it across all the available brokers. So in this case, we should have a replication factor of 3. So we are choosing, hey, segment 1 is replicated in bookie 1, bookie 2, and bookie 4. Segment 2 is replicated in bookie 1, bookie 3, and bookie 4, and so on and so forth. So that should answer your question of how the partition, how the things are mapped between the broker and the bookie. This metadata about where a particular segment lives, in which broker, and so on and so forth, is the metadata of the topic, which is kept in, part of that is kept in the Zookeeper. Someone made a comment, it's like HDFS. It is a real-time HDFS. You can sort of think about it as a real-time HDFS, absolutely. So we came from a storage-centric architecture when we are saying, there is no difference between real-time data and non-real-time data. It's all data, it's all events, right? And therefore, they should not be treated as different. They should be treated as one. So the minute data comes in, you should store it in one place, and you should access it in one place. So data is viewed as streams, it's persisted as streams, and is accessed as streams. And that's what this essentially does, right? This is both a storage as well as a messaging thing worded as one. That's the reason why I called it as an event store. It's a storage, infinitely expanding storage for events. Remote question, Pulsar replacing Kafka. A lot of, the short answer is, a lot of the customers who are adopting Pulsar, there are multiple different people. Some people, are more interested in the queuing aspects of the Pulsar, and they like the fact that both queuing and streaming is done in one segment. A lot of the other people that come to Pulsar are people who are running Kafka, and are hitting, bottlenecks, whether it is in terms of the topic, number of topics, whether it is in terms of the topic sizes, whether it is in terms of durability, whether it is in terms of the size of the streams that they can host, and so on and so forth. And they are actually they are replacing their Kafka systems with Pulsar. So the answer lies somewhere in between. Yeah.
How are things joined together? A lot of sensors come in at like 5 milliseconds, 7 milliseconds for another sensor, 31 milliseconds. A lot of times it helps to have a fuzzy join, so you have a record. That's the closest time frame. When you're doing these segments, does that cause problems? So the question was, different sensors are sending data at different intervals and so on and so forth. How is a logical view of that data maintained? Pulsar has this concept of event time and so on and so forth. So you can actually tag your events, your messages based on what event that happens according to the event time and so on and so forth. So that is preserved inside the messages. But the ordering of the messages is based on the order in which it was received by the broker. So that broker is acting as a gatekeeper of when it was received. So the ordering of the messages inside the partition and inside each segment is based on when the thing was received. Is it possible to do a fuzzy join to create one record across all the sensors?
The question was, is it possible to join multiple different sensor data into one thing? So that is where transformations come into the key, right? So you can basically think of each sensor having a particular stream and so on and so forth, and then you're basically taking all of those sensors, you're applying some sort of a windowing function wherein you're saying, okay, which of my functions, which of my sensor data are arriving at the same times, and then you can say, okay, what is the order and so on and so forth, or what is the enrichment data, what is the composite record that comes out of this enriched data, and then you can store that in another transform topic which composes of the fused data that you're talking about. There was, yeah. The question was, for the transformations, do we keep track of the old data and the transform data? We keep track of both, right? So every topic or every stream, as we sort of call it, has its own retention policies, right? So you can say that, hey, I want to keep my original raw data only for 10 days, but I want to keep my transform data for a month or a year or whatever it is. So you really can actually say it on a per namespace, per topic, per tenant basis. Topic and tenants are some concepts that I'll come a little bit later, but you can apply that on a per topic basis, and so the Pulsar retains the data according to the policies of that particular topic or namespace or tenant. So as you can sort of see, the take is completely different. Now, why this shines is that, as you can sort of see here, if you have 4 broker nodes and only one partition, only 3 brokers are really active in Kafka. On the other hand, with us, with Apache Pulsar, all the data is actually peppered across all the brokers, all the bookie nodes. So this also means that we can actually use the storage of all the bookie nodes across the cluster. And this has implications both for writing as well as reading. Now, if you're reading, we can actually do a segment by segment read. And because the data is peppered across all the various bookies, when you're reading a particular stream, you can actually utilize all the effective read bandwidth available from all the disks of your cluster. Right? That is a huge throughput improvement as opposed to reading from just one machine and therefore maybe 3 machines if you have a replication factor of 3 inside Kafka. So that's another huge differentiation when you're talking about your read throughput. It also has implications with respect to write availability and read availability. Essentially, if one of the broker machines go, for instance, the lead machine go down, you're kind of hosted in Kafka. You have to have another guy take over the lead, and then you have to make sure that the new guy who comes up as one of the followers is completely up to date with the new system. That's no longer the case over here, right? Because what happens is if a bookie goes away, the data is still present. In at least 2 copies of that are present in other bookies. So everything, all the read and the write operations go through, right? And when the new bookie is added, automatically new segments sort of start getting peppered into it. And so in more a sense, it acts like how HDFS kind of handles its load. It peppers the load across all the available bookie machines. Brokers are stateless, so there is no state stored in the machines. So if brokers go down, clients quickly reconnect to another broker, and other brokers take over the ownership of particular topics and so on and so forth. And all of this happens in milliseconds. Yes, question?
In the picture on the right, where do the brokers appear?
In the picture on the right, where the brokers appears, brokers are the one, you can sort of think about the logical partition as the broker level. So the broker is seeing the partition, and the bookies are only seeing the segments. It's a broker that's actually taking a partition, plugging it down into segments, and then writing these segments as a bookkeeper client to the bookies.
And so while they're doing that, they're holding the data, right? So there's some window where the broker failed, they will lose.
So the question was, while the bookies are writing the data, the broker is holding some buffer. So the broker actually has a cache, right? So for instance, the broker, one of the aims of the broker is to serve its consumers as quickly as the data arrives, right? So the data arrives, so a producer produces a message, the message goes to the broker, and the message, after it is returned to the bookies, then gets going to the consumers right away, right? So now, what might happen is that if the broker goes down, let's just say before it actually sends an acknowledgement to the producer, then that means from a producer perspective, the data was not written. Because producer produces it, waits for the acknowledgement to happen. If the acknowledgement never comes in, that means that somewhere along the pipeline, that data never got written. So the producer goes and produces the data again. But if the producer got an acknowledgement, that means that the data was persisted in the bookies. And at that point, if the broker goes down, that's fine, right? The consumers quickly connects to the other broker. The data is anyway persisted. So we lose the caching side of things. So for a while, you probably have higher latencies. But there is no rebalancing, et cetera, that's needed. Things work seamlessly. Yes? So the question was, there could be a problem wherein the data is actually written in the bookie, but the bookie never responds back, right? And the broker never gets a response from the bookie. So the thing is that if the broker doesn't get an acknowledgement from a bookie, that basically means that the broker never adds it into the metadata, right? After all, it's the broker that's maintaining the metadata about what is the segment and how much is the segment return and so on and so forth, right? So if the broker doesn't get intimation from at least 2 bookies, right? From its perspective, its data is still not written yet. So it will time out or whatever it is and try to find another healthy bookie and try to write into that bookie, and only when that bookie responds back will it acknowledge back to the producer as well as update its metadata, right? So the data that it was written on the old bookie that did not respond is basically garbage data, which is no longer useful. It's not part of the system anyways. So the bookies, after all, after some point will just garbage collect the data.
But the question was, everything went fine. It's just the last acknowledgement from broker to the producer that failed. And producer sends back the message thinking no acknowledgement.
Okay.
And now, what is the intelligence that this data was already processed?
Okay. Okay. So the question was, what happens if the message got written into the bookie responds back, but before the broker can actually send its acknowledgement back to the producer, the broker dies, right? It really depends on what is the guarantee that the producer is writing in. Now, let's just say in the case of, at most one or at least one, the producer doesn't care. The message will be rewritten. From its perspective, it never received an acknowledgement, which means that the write failed. So it will rewrite it again, which means the consumer will get it, twice, right? So that is the concept of at least once, at least once or at most one semantics, based on whatever is there. Now there is another semantic called effectively once. So in the effectively once, it's based on sequence IDs. So basically what happens is, every message is tagged with the sequence ID, incremental sequence ID. And so when the broker gets the acknowledgement from the bookie, it updates its metadata. And so in the metadata, you can say that, okay, the last message that was written was message 2 or something like that, right? And it dies. The producer says, the broker has died, let me republish the message. So it will republish the message again with with message 2. At that time, the bookie says, this is a message that I've already seen because my metadata, whether it's the same broker or different broker, it doesn't really matter because the metadata is persisted across the brokers. Whatever broker that is now in charge of the topic will say, okay, I've already seen message 2. This is an effectively once publishing, so I'm going to safely ignore that message, and I'm going to only start writing your data from message 3 onwards, and so on and so forth. The metadata is stored inside Zookeeper.
So there is no replication there, or if there is any chance that will die?
So the question is more about the availability of Zookeeper. A lot of this hinges on the availability of the Zookeeper. Zookeeper is the ultimate thing which, one of the guarantees that Zookeeper provides is that data is never lost and that data is always consistent. So that's a paradigm that we rely on, and Zookeeper is typically based on of 3 nodes or 5 nodes or even 7 node clusters. So it's the chances of all of that failing is not, that's don't. There is a project actually inside to get rid of the Zookeeper dependency. Because we actually provide our own storage, we can actually use some of that, but that is in very early design stages. It's not yet there for production. Yes? What was the question again? The size of the partition? Size of the segments. The size of the segment is configurable. By default, it's a gigabyte, if I'm not mistaken. Okay. And the second question was? Can you repeat it a little louder? I couldn't hear. What is the end-to-end latency from producer to consumer? It's a 99 percentile of 5 millisecond. This is just producer-consumer, right? So there is a producer writing and there's a consumer responding. So you're just putting a timestamp on the producer and measuring the timestamp at the consumer and then doing the. So one of the things that Pulsar provides is a very flexible messaging model. As I was mentioning earlier, systems like RabbitMQ provides a queuing-only model. Systems like Kafka provide only a streaming-only model. We provide both the streaming as well as queuing model. So that is accomplished by this called as messaging model. So depending on what you want to consume, you can have a different kind of subscription. So in this example, consumer A is saying, I want an exclusive subscription on this particular topic. What that basically means is that only consumer A will get all the messages. Any other consumers who are using that particular subscription name will not get any messages because only consumer A will get the messages. Typically, what is employed is a failover, wherein you have consumer C1 and consumer C2, C3, Cn, whatever. And that's called as a failover, wherein you're saying, okay, there is a particular subscription, I'm going to subscribe it in the failover model. So the guy who first connects, let's just say C1, is the one who is the consumer of the event. All the other consumers are hot standbys. They don't get any messages. But as soon as consumer C1 fails, as detected by the broker, the broker starts giving out the messages to consumer C2. So it's kind of a hot standby mechanism in some sense. And in both of these cases, there is at any point of time, there is only one particular consumer of a particular partition. So those are the streaming use cases, the analytics use cases, and so on and so forth. On the other hand, for the queuing model, we have the shared subscription. So you have a subscription and call it shared. So what that means is that some messages will go to consumer B1, some messages will go to consumer B2, and so on and so forth. And it's kind of round robin or whatever it is. So you get batches of messages, and as you acknowledge the messages, more messages will be pumped to whoever it is that acknowledges those messages. Multi-tenancy, so this was something that was built in from grounds up. So a single Pulsar cluster is, it can be as tiny as a single on a single Raspberry Pi, or it can be a data center wide thing. It can actually support the entire enterprise. And the way it's done is the concept of what's called as the property or namespace or tenants and namespaces. So think of properties or tenants as your divisions. Let's just say your advertising division, your marketing division, or your engineering division, your data science division, or whatever it is, right? These are different tenants. And tenants are usually have some carving out of resources. You can say, hey, tenant A, which is advertising, will get, some sort of a QoS guarantees. We'll give you, 1 gigabyte per second kind of a throughput across all your subscriptions and so on and so forth, and you'll get the priority serving. On the other hand, for marketing, maybe we'll give you best effort or something like that, right? Inside the properties, there are these namespaces, and namespaces, you can sort of think of it as applications. So let's just say you're doing advertising and you have a particular applications, which is your real-time serving real-time analytical applications and so on and so forth. And inside each of the namespaces are a bunch of different topics. So you have clickstream event as one topic. You have website website views as the other event as the other sort of topics and so on and so forth. So as you can sort of see, it's a 3-layer architecture wherein there is a topics at the lowest level. They are all bunched in namespaces, and namespaces are bunched into properties or tenants, and all of this acts as one single Pulsar cluster. So, and these all of them are supported, are served by hundreds, potentially thousands of brokers and bookie combinations. And as such, you can actually have just one Pulsar cluster managed by just one Pulsar ops team across the entire big enterprise. So for instance, a company as big as Yahoo, now Verizon Media, Joe can probably talk more about this, has a single Pulsar cluster across their entire data center, for instance. Yes?
So you mentioned you can put a Pulsar cluster on a Raspberry Pi, probably with 1 gigabyte segment size. It's not going to be able to handle too much. Is there anybody out there that's actually doing that?
So not particularly in Raspberry. So the question was, what's the use of running Pulsar in Raspberry Pis? What's the, what are the use cases? The reason I took Raspberry Pi is that there are a bunch of IoT use cases where you have what are called as the mini data centers or mini micro data centers, which are spread throughout the world. And there is data coming in, there is processing going on, some sort of simple processing going on, and there is data actually being sent back from these micro data centers to the neighboring data centers and then to the bigger data centers and so on and so forth. And each of these guys are running in some sense a Pulsar cluster, and therefore it is actually able to morph itself as small as in those micro data centers. And then progressively get bigger and bigger as you grow from the local data centers to a global data center and so on and so forth.
The segmenting of data centers, as you kind of were describing, how does that, is that one cluster, or those segmenting, or are those layered clusters, or how does that work?
So segments is completely different. It is an internal implementation detail. The users are not aware of any segments and so on and so forth. Segments is a construct that we use internally to maximize our read-write throughput and read and write availability. So it's an internal, if you're just a user of Pulsar, you'll get all the good things about segments, as increased read availability, increased read throughput, and so on and so forth. You don't care, you're not even aware that you are consuming from this segment and so on and so forth. So as a user, you don't really know about segments. You're only concerned about cluster, which cluster my data actually resides in, what is my stream, how do I access it. Replication, geo-replication is one thing that's built in. In this example, there are 3 data centers, data center A, B, and C. There are producers, consumers, and these are actually consuming and producing essentially one topic. Imagine your Facebook. Your users are everywhere, right? Your users are in Asia. Your users are in Europe, in US, and these are usually interacting with their local data centers. But you still want to get an aggregated view of the entire event stream as it sort of appears, right? So Pulsar makes it possible by just configuration, right? You just say, hey, this is my event, and this event is actually replicated in this other data center, and so on and so forth. And so over here, what is happening is that you have these producers which are producing in all different data centers, and you have these consumers which are consuming from either of these data centers. And what the consumers actually will see is that they'll see all the events across across the topic, even across all data centers. Now the thing here is about the ordering. We guarantee that the data will appear as it is ordered within a particular data centers, and across data centers things can be interleaved, but that's okay. Right? Within a data center is what you really have the ordering, and we basically guarantee that. So so far we have sort of talked about Pulsar and so on and so forth. The reason why I brought Pulsar is because that is central to the Pulsar functions that we sort of talked about, right? So coming back, right, where we were thinking about, hey, programming these compute engines is, hey, very, very complicated. It's hard to understand. You need to really be experienced some time to actually really use effectively and efficiently these tools. And secondly, it's a huge, even if you understand, it's a huge maintenance headache and so on and so forth. It's really a big hammer for what mostly are small nails, right? So how do we solve that? And one of the solutions is Pulsar functions. And what we are saying is that, your exclamation function, pretty much everyone is probably aware of it. You get a string, you attach an exclamation, and you send it back. Your exclamation function should look exactly like an exclamation function, right? It shouldn't worry about anything else. It shouldn't worry about attaching where the data is to be read and so on and so forth. It is just worried about the code. And the code is, hey, you get a string and you're returning a string, right? And note, I'm not using any new API. Java util function is something that's there in the Java SDK. If anyone who's programming in Java 8 already has access to Java util function. Right? So he or she can just simply open this without any API dependency, build a jar out of this, and submit it. So it's supposed to be as easy as that, right? No need to learn any extra API, right? So as soon as you know, we can have the similar thing in Python, wherein in Python, you just have to write one Python function, that's all, a process. And then that process, it'll take some input and it may optionally have an output, and that's about it. So if you know Python programming, you know how to write a function, that's about it. You don't need to know any other complex, data science language or data engineering API and so on and so forth. It's optional. We do provide that, right? But out of the start, to start off with, anyone can and everyone can actually just write a function and get going, immediately. What this function says is, hey, I'm taking a string. Basically, I'm treating all my inputs as string, and I'm also outputting string. And by definitions, we are programming in Java. Everything is type safe, so you get all the nice properties of type safe. If you're programming in Python, type safety is optional. We are having some sort of a type safety nature in Python as well. But that is kind of non-intuitive to the Python programmers who typically don't have the concept of a type. But in Java, everything is typed, so you kind of get that nice abstractions right away. On the other hand, we also provide an SDK, right? And this SDK allows you to do powerful and very interesting stuff, right? So and writing, here we are writing a word count example. Writing a word count example is not incredibly different from the exclamation function. We still implement a Pulsar function, right? And we still use the process. And what we are here doing is that we are taking a string, we are treating it as a sentence. We are extracting all the words, and we are actually saying, for every word that I encounter, increment a counter somewhere, right? So for a simple novice programmers who knows how to read and write Java function, he or she has no idea of data science, he or she has no idea of data engineering, he doesn't know about stream computing and so on and so forth. If you show him or her this program, most likely they'll be able to say, this is actually doing word count. Even if I obfuscate the function names and so on and so forth, he or she will be able to say, this is actually doing word count, because the logic is very, very simple, very, very intuitive, very, very out of the box. There is no other obfuscation or complicated metaphors that we use in flat maps and maps and so on and so forth. Everything just flows out of the box. Hey, we are taking a string, we are splitting that into words, and then we are incrementing one counter, one for every kind of word. So as I said, the SDK that we sort of provide, functions API, has a bunch of advanced properties, like it has inbuilt state associated with it. It allows you to get which topics you're reading, which topics you're writing to, and so on and so forth, right? All these things that might be that you might need for a little bit more complex level of stream processing. So how are these Pulsar functions executed? And a function is executed on every message of input topic, right? So when you run this function, you say, hey, this function takes in this input topic. And by the way, a function can take in more than one input topic, right? So so functions support many input topics, as inputs. And at that time, what happens is that the function is executed as soon as a message appears on any of those input topics. The output of the function goes to another output topic. So you can specify, hey, send this output to this particular output topic, and the messages go to that particular output topic. You can see in the previous function, this function actually had no return, right? It was actually just a void, which means that functions need not return anything. They need not write anything per se to a topic, and so on and so forth, right? Functions can update a database. Functions can go and call other interfaces and so on and so forth. In that case, they may or may not have any anything to output per se, so they need not have any output. And all of this, how do I treat the message as string versus an int versus some kind of a JSON structure and so on and so forth, is handled by schema registry. So schema registry is something that's built inside Pulsar. So it's not an add-on or something like that. It's included, bundled inside Pulsar. So when you create a producer or when you create a topic, you can basically say, this is my topic, and my topic consists of messages of this particular type. You give it a POJO, for instance, if you're using the Java language, and we use that POJO, that Avro in whether it is Avro, whether it is JSON, whether it is protobuf, and so on and so forth. We support a bunch of different POJO types, and so that's how the input data is treated. You had a question?
Is the topic passed in along with the input message?
Yes, so the question was, is the topic passed in along with the input message? So if you look at the interface, the input is what the input message is, right? And the context has a bunch of parameters. So one of the functions is, hey, what is the current input topic? And that gives you, hey, which is the input topic that this message kind of belongs to, and so on. Yes?
So, is there a possibility of swapping the functions in and out on a live system? Basically, hot swap, code swaps. I know I write a new function, I want to update the version of the old function, and so on and so forth.
Yeah, so the question was, is there a way to hot swap? Is there a way to update a running function? Yes. So I'll probably touch a little bit on it later, but you can create a function, you can update a function, you can delete a function, and so on and so forth.
How do I make sure that the output data is tied to a certain version of the function? Is there a versioning of the data of the output or something? The only thing right now we enforce is a schema. So once you sort of, let's just say you're writing a particular, let's just say you're writing integers into your functions, and then you say, oh, I'm going to update this function and I'm going to output floats or doubles and so on and so forth. That would be flagged upon as soon as you sort of start the function. We'll say, hey, you know what, schema mismatch and so on and so forth, right? So we try to catch that in terms of the type of the messages that we are stored. With respect to which version of the functions we are running, that part is still to be flushed out. Right now, we don't really keep an accurate track of which is the function version that you are. We have a function version, but we don't have straightforward tools to say, hey, what was function version 2, what was function version 1, and so on and so forth. That's, again, a roadmap item. But hopefully that answers your question. So probably similarly around the bookies too. So some books get updated with the new version of code, some are with the old one, and so forth. If that should be
Yeah, so the observation was when you are doing these updates, there'll always be some instances will be running new code, some instances will be running old code. So that really depends on the semantics of what you're trying to do. If you want to update all at once, you can always do a delete and followed by a restart. That always works. Most of the time you want to do a rolling upgrade kind of a thing wherein you're saying, hey, this is new code, this is a far more efficient model, or this is this improves the function in some way, but I don't want to disturb any kind of my regular processing or regular systems, regular downstream processes, so update the instances every few seconds or so on and so forth, right? So in that case, you'll have a rolling upgrade kind of a thing, wherein during the upgrade, yes, there will be some instances running the old version, some instances running the new version, but that probably is handled by your downstream consumers in some sense.
Looking at a typical functional programming in that context, how the global state is supported? Is there a support for global state, shared state? And the other related question, you mentioned something about updating the database. So what about the side effects? Because your functional programming won't allow you the side effects, right?
Yeah. There is a twofold question. The first question was, what about the state? Where is the state kept? What is the semantics of the state? Is it shared, and so on and so forth? Why don't I come back to that? There are slides. As opposed to, I'll come back to the other question also, which was, what about the side effects? We'll come back to both these questions as I take care of the other things. We'll come back to that. So schema registry will take care of the schema serialization and deserialization. Okay, coming back to processing guarantees, right? So we support all the typical processing guarantees, at most once, at least once, effectively once. Essentially what it means is that you can basically say, hey, execute this function at most once, which means that as soon as the message is arrived inside the framework, we acknowledge it. Maybe the function has executed on it, maybe the function is not executed on it, that's fine, which means that if the function dies for some reason, I will lose some messages, but that's okay. That's at most once. In at least once, what we sort of make sure is that we only acknowledge back to the Pulsar after the function executes. So that means that if the function executes and if it dies before if you die before acknowledging, yes, that message will be replayed back again, but that's the at least one semantics. Effectively once, we again you reuse the effectively once mechanism that is already inbuilt inside Pulsar for the effectively once semantics. So essentially we sort of make sure that the consumer inside Pulsar function receives the message only once. And so on and so forth. Now, what happens to the side effects, right? So your function is actually writing to some other external database, or it's actually writing to the state, which I'll come back in a second. What happens to that? Those are side effects. Currently, the effectively once, for at most once and at least once, you probably don't care because your counter gets you either undercount or you overcount, and that's probably okay because that's the semantics of at most once and at least once. But for effectively once, currently that has to be sort of taken care of outside the system. You have to be aware of the side effects. We are working on a system wherein within our state, which I'll come back, we are trying to mingle both the state updates as well as the output updates in one single transaction, but that is still a work in progress. So that will actually guarantee a truly effectively once with side effects. So one of the things was functions actually have state. So for instance, if you move back to the word count function, right? Apart from counting words out here, what this function is doing is that it's saying increment a counter, right? Now, where is this counter? And who maintains it, and so on and so forth. Because we are essentially an event store, a stream store. So we have this stream store layer wherein we manage the state for the function. So instead of writing this on to another external system like a memcache or a Redis or something like that, you can actually use this built-in, aka key value storage kind of mechanisms that we have built in on top of Bookkeeper. So the state store is actually provided by that, what we call as a stream store. It's a simple library that we have built around Bookkeeper that kind of exposes a key value kind of interface to the data, and this is a global state, right? So essentially what this means is that a function updating a key value. Let's just say I'm a function, my name is foo, and I write a key called bar. So my foo/bar is my global key, and it has a value of something. It could be either a counter, or it could be some sort of a state, or some bytes, and so on and so forth. That is now visible across both these functions, other functions, or outside the functions. So in that way, for instance, you can actually query that using a REST interface and saying, hey, what is the current count of the word umbrella or something like that, right? You can, so that this way what you can sort of do is that you can write very quick dashboarding applications wherein data is coming in and you are basically incrementing counters, for instance, how many times umbrella appeared and so on and so forth, and there is a dashboard that is periodically querying using a simple REST API, hey, what's the current count of umbrella, and updating its chart. So that's a typical use case of how the state is effectively managed inside the functions. Currently, as I said, this state is still a side effect. So that effectively means that if you're running your function in effectively once, you still can have overcounts. But we are working on transactional support in Pulsar. Transactional support will allow us to we can write to multiple topics, either all at once or all nothing. Once that support is there, we will plumb in the state along with the transactional support to make it truly effectively once, wherein the state will be updated only once. Yeah. Can you please repeat the question again, given the size of the data?
Given the complexity with how you're managing the data, do you have any QoS artifacts? Like, are you able to manage the QoS of requests effectively? Because you said 99% with 5 milliseconds, which isn't that much, right? It's only 2 nines. So is it a fat tail? Is it a thin tail? Is it a bimodal distribution? Do you end up getting thin queries a lot of times?
Matteo, do you want to comment a little more? The question was more about the performance characteristics, about the read, the latencies especially. What sort of distributions are we talking about, and what factors affect those distributions? By the way, this is Matteo Merli. He's one of the co-creators of Pulsar.
Yeah, so I know the throughput depends on hardware, so it depends on the kind of how the data is with one single partition, multiple partitions, how you route the data to the folder.
Relatively simple model of taking data and breaking it into multiple stages and having each stage the data into dynamic. Now you're chopping it up or adding replication. You're adding all these events which require some sort of tuning or scheduling in order to happen. Schedule the segment creation, schedule which segments go on which server. If those aren't necessarily reliable, so you make it down and creates the issue. You might have some which has a lot of replication and some few replication.
So suggestion, maybe you guys want to take it offline after this? It's an involved question, and it's an involved answer, I believe. As I said, built-in state management. How do we run functions, right? Very simply, you can run it as a standalone application. So you had your exclamation example or whatever it is. Wherever you are, you can actually just run it as a JVM process. You can say Pulsar admin is actually an inbuilt a tool utility that we provide alongside Pulsar. It's a thin REST API interface kind of thing. You can say functions local run. Local run is basically you're running the function on your laptop or wherever it is you're executing this command. You can say this is my input, this is my output, this is my jar, and this is the class within the jar that actually runs my function, right? You just run it. This will basically spawn a JVM. Right? And now you can manage your JVM however you want, right? You can use your favorite tool to make sure that it is up and running and make sure that multiple copies of it are running across many machines and so on and so forth. Whatever tool is useful, whatever tool you're used to running to manage your processes, you can sort of use it, right? The biggest advantage of running this is that you can actually simulate your function right away, right? You don't have to run your system. You don't have to run your functions anywhere. You've written a sample code. You want to see how it works or whether it works and so on and so forth. This is a quick way of, say, running it on your laptop, seeing if the messages are consumed properly, are passed properly, and the output is correct and so on and so forth. And then if everything seems right, now you say, okay, this program, maybe I should be able to deploy it in an actual cluster, in an actual production setting, and so on and so forth. So local run is a way to basically mostly test and run them as a standalone application, right? Now, the more interesting one is running inside a cluster, right? So you can use the create, delete, and even update, which is not mentioned in this slide. So basically, you say the same thing as you said before, admin functions create, and you're basically saying, hey, create my function. I'm giving it an input, and I'm giving it an output, my class name, my jar name, and so on and so forth, right? So here, what we are saying is, hey, you specified a function. Okay, I'm going to name that function as exclamation function. The system automatically determines that, okay, I'm going to name this function as exclamation function, and it's going to take care of it, right? It basically, at this point, you're making a REST call to the Pulsar system. You're passing this jar. You're uploading this jar, and you're saying, hey, manage this functions. Now you can also say dash instances 10, right? You can say, hey, always run 10 instances of this function, right? Now your functions, is now going to be spread across all your brokers. Now you can actually run the functions in many different ways, right? One interesting way you can run it is that you can run the function in a threaded mode. And by threaded mode, I mean that you have the JVM, the broker, Java, the Pulsar broker is written in JVM. It's in Java. So if you're submitting a Java function, and you're saying, hey, run it in threaded mode, your function is actually running as another thread inside the broker itself, right? So imagine the broker process. There's another thread that's attached that's actually listening to the messages. Now you may think that that's actually might be a bad idea because hey, this is a broker, this is serving my production traffic. How are you running some untrusted code? I don't know what the heck the code does. I don't know what other side effects that it have. It may mess around my system. It may even destroy my system. How are we going to run this as a thread? It depends really on your use case scenario, right? For instance, in a lot of let's just say you're in IoT, you're running it on a very small data center, which on a very like a low resource kind of an environment, you cannot really spawn many multiple Java processors, right? You have to sort of optimize your memory, your processors, and so on and so forth, right? There, not everyone, it's not like your entire enterprise, your Google and thousands of applications, random applications are actually submitting your applications. You know what exactly the code that goes in, so it's okay for you to run these processes, inside the broker. That way, you'll achieve the smallest footprint and still be able to run in a constrained environment.
For the Raspberry Pi, how much memory footprint does Pulsar take? Because if you're processing data, you have your own user program, so that would be in the space after Pulsar.
That is true. So the question was in a Raspberry Pi, what is the footprint of the Raspberry Pi that we're talking about? I think we have been able to run the Pulsar as well as a couple of simple filtering functions in a Raspberry Pi of about 1 gig of RAM, if I understand correctly. And
does the Pulsar take 800 meg, 100 meg?
All of it is configurable. It really depends on what kind of load you're putting and so on and so forth. The Pulsar uses direct memory, so it doesn't really require a lot of heap and so on and so forth. So all the buffers, all the netty buffers that it receives are all inside direct memory and so on and so forth. So it manages the memory very effectively, very kind of natively, kind of like a C kind of thing. And if you're running your functions as threaded, then you're not having any kind of other JVM overhead and so on and so forth. So you're effectively running one single process. Inside the single process, you might have multiple copies of the data as the data is coming in. But again, depending on your throughput, if you're running maybe 1,000 messages per second, or even like maybe 4,000 or 5,000 messages per second, each message is like a kilobyte long, you should be able to easily sustain that throughput, that kind of a throughput inside a Raspberry Pi.
So you can do it at 256 to 512 meg. 256 to 512 meg.
That's a minimum that we have been able to compress down to 256 to 512 megs. So as I was saying, functions can be run as threads. Functions can also be run as processes. Essentially, what this means is that these functions are run as processes alongside the broker process. Now, so this gives a little bit better, separation. Processes don't really have accesses to brokers' memory, so it's a little bit safer. But at the same time, it is still problematic because, hey, your processes is still on the same physical node as the broker. Right? Like what if it does some malicious stuff? What if it rewrites the root partition or something like that? What are you going to do and so on and so forth, right? Because ultimately functions are user code, they are untrusted code and so on and so forth, right? And there are various ways to sort of do that, right? You can actually run it in containers, which I'll come to it a little bit later, but you can also sort of designate a bunch of your nodes as processing only nodes, right? So some of the brokers, you can say these are only for running functions. And these nodes should be not acting as brokers, but they should be acting only for running functions. What that means is that anytime you start executing a function, only those kind of nodes will be used for running functions. The other nodes will be used for doing the actual messaging and so on and so forth. Yes, you have a question?
Sure. Does Pulsar automatically profile itself and self-optimize?
The question was, does Pulsar self-inspect itself and optimize? I don't think that's the case, Matteo. Do you, or Joe maybe? To some degree. Okay. Okay. Yeah. Yeah. Okay. So the way it works is that all the topics are distributed across the entire all this set of brokers. So if some topics become hot, Essentially, there are, or some brokers become hot because there are too many consumers or too many producers producing it. Pulsar automatically detects this and says, okay, let me split this, and some other brokers will handle some topics, and this brokers will now have lesser number of topics, and therefore that's how the load is kind of distributed across the other brokers. So that's the effective healing mechanism. The other cool thing is that you can actually use external runtimes for managing your functions, right? You can configure your brokers and saying, you know what, when you create the functions, actually create them as Kubernetes pods and let Kubernetes manage things, right? And Kubernetes is good for it because it knows how to manage these pods, it knows how to manage the memory, the things, all the scheduling aspect, and so on and so forth. Let's broker doesn't manage this. All that logic should happen in Kubernetes because that's what it's meant for. We can sort of do that, right? So the user doesn't care. The user will just simply create the functions, and underlying you're actually configuring the broker saying, hey, when users submit the functions, run them as Kubernetes pods. And Kubernetes manages the lifecycle, but Pulsar manages the lifecycle of the functions. So this is very ideal if you want to like event-driven microservices. This is a very good way to sort of deploy your functions, and these functions could be serving, topics are modeled as events, and then these functions are actually processing something and writing back the output events and so on and so forth. So in some sense, the classic microservices architecture on a Pulsar can be done using Pulsar functions. Yes? What kind of ordering guarantees do we have? So I think I went over this. Pulsar has both the at most ones, at least ones, and effectively ones. So in at most ones and effectively, in at most ones and at least ones, there is no guarantees. But in effectively ones, there are guarantees. Effectively ones, we basically guarantee that all the events of a particular partitions are handled in the order of the partition, and they are all handled by only one particular instance of the function. Yeah, so the way it happens is the following, right? By default, it's probably at least one. It is at least one. So what that means is that if you run 10 instances of this Pulsar function, right, you are having 10 consumers essentially reading from the same topic, right? But since you are running in at least once, if you're running in at least once or at most once, you don't really care about the ordering. You want the things to be processed. And whether or not you process 2 times or many times or no times, that is, it's okay. So at that time, what we do is that we use the shared subscription, as I sort of mentioned about, right? But when you're saying effectively once, that means that you suddenly the ordering, etc., and the fact that you have to process every topic at least once, only once becomes sort of important, right? So we tie that thing with the effective. When you say effectively once, you say, oh, this is a failover subscription. So now what we do is that if the topic has 100 partitions and you say, hey, run 10 Pulsar instances, you can sort of say that each instance roughly handles about 10 partitions. And so one partition is handled by only one instance of the Pulsar, and all of the events come in it in a logical, in the same order as it was in that particular partition. Yeah, so the question was, if you have 2 Pulsar functions, so it could be the same code, but they are treated logically separately. There is no guarantees of ordering. Yes, from a Pulsar perspective, these are 2 independent functions. Whether or not they share the same code or they have different code is immaterial. When I talk about one function, that means it is one function. You can say that 10 instances of the functions can be running just for load balancing or whatever it is, right? That is the concept that Pulsar knows about. So you're saying, okay, this is one function. I'm calling it function A. Functions are named by their fully qualified name, right? Tenant, namespace, and the function name, right? So a particular function name has 10 instances, right? Now that is the construct that Pulsar knows about, right? Now so what Pulsar does is that there are 10 instances of the same function, with the same function name, each having a unique function, each having a unique offset, right? This is function instance ID 0 and instance ID 1 through 2 and 9 and so on and so forth. So those are the things that Pulsar manages, and which of the instances get what data is determined by what kind of delivery guarantees you want. If you say effectively once, we usually go and say, okay, this is an exclusive subscription. We are going to, each of these instances will have an exclusive subscription using the same subscription name.
Like, say you wanted two operations and one depend on the result of the other, is there any way to make that happen? Or would you just have to wait for the first one to return before you send the second?
So the question was, if there are two operations, one returning one as the input to the other, how do we
Like you're modifying the state of the system, side effects.
Can we take the other questions offline? Just go back up the slide.
we'll touch back offline. I think we are running out of time. I'm going to quickly wrap up here. So stepping back, powerful, complicated systems have their place. We are not saying we're replacing Spark. We're not saying we're replacing Flink and so on and so forth. But in our experience, a significant majority of the problems are fairly simple, ETL and so on and so forth. For that, you don't need to actually use a very complicated tool like Flink or Spark. You should use functions. What are the most basic use cases? Data cleaning is by far the biggest use case. Most of this is mundane work, right? And typically, this is all handled to consultants, especially in big banks and so on and so forth. A lot of these things are, simple work, and they want to maximize the value they sort of get out of this by farming out this to less experienced or less qualified people and so on and so forth, right? So these people typically know just basic programming. So if you want these guys to be getting productive from day one, making them learn a complex system like Spark or Flink is an overkill. For them, they should just be knowing how to program, and that's it. They are off to go, right? So this is a very good candidate for basically increasing your efficiency of all the kind of programmers that you have you have available. IoT I talked about. We can have local actions. Let's just say you have a bunch of different micro data centers, each generating some data. You can have local data centers which are doing some kind of filtering, some kind of enhancing, and then sending this data back to a global data center where we are kind of meshing all of that together for further analysis, right? Pulsar functions is a very good use case wherein you can do all those transformations, etc., very simply in a low memory footprint kind of environment. Model serving, right? A lot of the times you create a model using some complicated offline process, but now what, right? You can sort of embed this model into a Pulsar function, and this function is going to execute every time a new event comes in. Like a photo processing event, you're essentially extracting features. The feature extraction is nothing but a model, right? This model has been trained by using some complex data, using a complex process, whether it is TensorFlow, whether it is Spark or something like that, that's separate. But now once the model has been created, how do you deploy it, right? How do you actually use it to classify or to actually extract features out of images and so on and so forth. Pulsar functions is a very easy way to sort of deploy them on incoming requests. So where are we? We already have support for Java and Python. These are the first class support. We have Go in progress, so we want to have Go in 2.4, which is our next upcoming release. Next up is JavaScript because there's a huge community of developers. As you said, the more we sort of open this up to people, the more people will be interested in stream processing, and a lot of things that they currently have to learn Java or even Python, people should be able to do that in other languages that they're more familiar with. Other things are functional composition APIs, authentication authorization. Currently, the story is a little bit weak. We are working on that with the functions and so on and so forth. So that's in a nutshell. My talk about functions would be happy to take questions. We're probably out of time, as saying, but I'll be here available. My colleagues are all here available. Feel free to back. Thank you guys for inviting me and having the opportunity. Thanks a lot.
Happy to have the meeting going on longer because questions and things. I just have to leave because I have an India team meeting at 9 o'clock, so I have to do my status with my team. I'll do a drawing. There's 2 books we can choose from.